Good morning, everyone, and thank you for tuning in to our webinar today on human 3D post-estimation from videos, challenges, and solutions, presented by SGInnovate and N-CRiPT. My name is Brian, and for those of you who don't know about us, we are a government-backed investor in Singapore with the mission to build deep tech innovations. At SGInnovate, our work involves connecting with the global deep tech ecosystem, working with entrepreneurial scientists to bring their innovative research from lab to market, as well as developing deep tech talent. Today, we have an amazing presentation by Associate Professor Robby from N-CRiPT, who will be discussing existing top-down and bottom-up approaches of human 3D post-estimation and more. I would also like to encourage our audience today to share their thoughts on this topic and engage with our speakers by using the Q&A box below. And now, with no further ado, I'll pass the time to Jitin from N-CRiPT. Jitin, please.
Thanks, Brian. Good morning, all. I'm Jitin Vacheri. I'll be your moderator today. We at NUS Center for Research in Privacy Technologies, or N-CRiPT for short, are happy to partner with SGInnovate to bring this webinar to you. N-CRiPT is a strategic capability research center in privacy-preserving technologies, aiming to spearhead research in 3 core pillars, namely privacy preservation along the whole data lifecycle, privacy preservation for data with emphasis on unstructured data, and privacy risk management. This webinar is part of N-CRiPT's public seminar series through which we hope to showcase our research and expertise in emerging privacy preserving technologies and issues. This morning, our speaker, Professor Robby Tan, will be discussing the technical challenges and the state-of-the-art technologies that can be used to analyze privacy information in videos related to human actions and poses. Professor Tan is an associate prof at Yale NUS College and the Department of Electrical and Computer Engineering, National University of Singapore. His research interests include computer vision, deep learning, and machine learning, particularly in the domains of bad weather, low-level vision, human motion analysis, and fundamental problems of deep learning. Without further ado, I would hand over the time to Professor Tan. Professor Tan, please.
Yeah, thank you, Jitin, for the introduction. All right, so I will share my screen. Okay, so the title of my talk today is on human 3D poses from monocular videos, challenges and solutions. And first of all, I would like to mention our goal in this research. Our goal is, as you can see here, that given these monocular videos, video from one view, we want to generate the 3D poses of this target person. Okay. But not only a single person, but we also address multiple persons as well. So as you can see here, given these frames here, this is one of those frames that we have. Actually, this is video clips. Then we want to generate the 3D. And as you can see here, if we can have the 3D, then we can change the viewpoints from 0 degree, which is the same as the degree from the image, the angle of this camera here. And also we can change the view, for example, the viewpoints of 45 degree or 90 degree. So having this 3D giving us more information about the action of the persons and possibly the gait and the behavior as well of the target persons. All right, so this is the end goal of our research. Now, why these 3D human poses are important? Well, the practical reasons is because there are many applications for 3D human poses. And this practical application can be in the forms of human-computer interaction, like Kinect, for example, or augmented reality, and video analytics, which is quite important here in this N-CRiPT project, because this can be used for visual surveillance, gait or behavior analysis, action recognition, activity recognition, patient elderly monitoring system, and so on. And this is really the core of privacy in video. And the next application is visual performance analysis, for example, in sport or physiotherapy. And the other application is robotics, and many other applications. So 3D human pose estimation are important for us, for human, to have this capability, and also very important for computers. All right, scientifically, the human 3D pose estimation is challenging, still an open problem, particularly for monocular videos. I will explain later on what are the challenges. Okay, so this is the video that I can give you an example here, that we have this kind of 2D pose estimation from single video by an existing algorithm. So as you can see, the state of the art for the 2D is quite good already, right? For the 2D, we can have a good estimation of the poses. Although if you look at the details, for example, this person here at this corner, the estimation is not accurate yet. So for example, the leg here and the leg behind cannot be estimated. So it seems to be good, it seems to be robust, but if you look more details, there are a lot of different problems, different challenges still there, right? So this is research in 2D pose estimation, which is very important for 3D pose estimation as well. Another kind of research is in this kind of what is called 2.5 pose estimation. In 2.5 estimation, as you can look at this image here, it is somehow give you the 3D effects, but it's actually not 3D. This is actually still 2D, similar to this one, but with more visualization. So basically, they just wrap the 2D estimation with some surface. Right? So, and if we can do this, we can have an application like this, for example. So this is the surface that is put on top of the 2D. So this is not a 3D at all. This is still 2D. Only this surface, the mesh, is put on top of the 2D. So in other words, with this application, we cannot see what is behind the person. So we cannot see, for example, the skeleton of this person behind this, because there's an occlusion. Right. So the difference between this 2D and 2.5D pose estimation with ours is that in 3D pose estimation, we can have a full view on the skeleton. And this have to be independent from any occlusions. In other words, even if there is some occlusion, the 3D estimation should be able to estimate the skeleton or the poses. Okay, so this is the difference between 2D and 3D pose estimation. Right, so this slide will explain further on the difference between 2D and 3D. As I mentioned, in 2D, it's look like very nice, right, for this kind of estimation. But as you can see, the left hand is occluded by the body of this lady. And that's the limit of the 2D pose estimation. They cannot estimate something behind the body here, and in this case, the arm. But in 3D, we should be able to do that. We have to be able to get this pose of occluded parts. The same as this leg here. The leg here is somehow partially occluded, and we should be able to get the skeleton of this pose. Okay. So that is the difference between 2D and 3D human poses. Now, why these 3D poses are challenging? And what are these challenges? Right? One of the main reasons is that the 2D pose estimation can be inaccurate. Especially when the video is degraded or in showing a complex scenes. The video has this kind of complex scenes. Then the 2D pose estimation or 2D human detection can be inaccurate. And this will affect the estimation of the 3D. I will explain that later on in the next coming slides. And the other challenge, which is the main challenge that we want to focus on this particular research that we have, is the occlusion. Occlusion includes self-occlusion, like what I mentioned just in the previous slide, and also interperson occlusion. Interperson occlusion means that one person occludes the other person. And the other problem is out of frames, means that the person is partially shown in the image, but not fully. Right, so aside from this occlusion, we also have a problem of limited data. Means that we have a limited annotation. Right? So this is the fundamental problem in deep learning. If you don't have enough annotation, especially for rare poses, then it will be difficult for us to train a network. And the other problem is limited variation of poses and limited number of poses. So I can give you an example of a limited number of poses is gymnastic poses, because these gymnastic poses are not quite common in videos. Okay, so the other problem is a bad input data. But input data is like blurry, low resolution, small scale, low contrast, low light, noise, and so on. And all these are the challenges that we have to face when we are trying to get the 3D pose from video. So this is the basic pipeline that we have. So given an input image, we use the 2D joint estimation. And after we get the 2D joint estimation, we will have this 2D joint or key points. In the later slides, I will use key point instead of joint. But when I say key points, it means these points here: the ankle point, the knee point, the hips point, and so on. Okay, so there are 17 points that we have to estimate in this single frame. And once we have these key points, we then use our 3D pose estimation, our 3D pose module, to get the 3D pose. The 3D pose will include the joints, the 3D joints, and also the 3D bones. All right, so this is the basic pipeline. And for the 2D joint estimation, there are two approaches. One is called top-down approach. So top-down means that given this kind of frame or image, we do the human detection. So we get these bounding boxes, and then for each person we have a bounding box, and from this bounding box we estimate the key points here. And once we have the key points, we can draw the skeleton. And this is done subsequently person to person. So that is the idea of the top-down approach. Another approach, so this is an example of the two top-down approach, which is called RMPE. So here we have human proposals in terms of the bounding boxes, and then from these bounding boxes, we estimate the joints. Right, so aside from the top-down, we also have a bottom-up approach. Bottom-up approach doesn't use any bounding boxes, doesn't use any human detection. What it does is that from the input image like this, we estimate the joints or the key points immediately without identifying the person. So these key points here are not colored, meaning that we do not know whether this belongs to person, the male person or the female. And once we have the key points, then we try to arrange which one connect to which one. And then based on that, we can identify the persons. All right, so this is the example of in the literature of the bottom-up approach, which is called open pose, which is a popular approach in this field. So given an input image like this, for example, then we get the key points. There's a lot of key points here. And after we get the key points, we do the path affinity. So we try to connect which one is more makes sense in terms of the connection than the others. Right? So once we have the path affinity, then we can do the matching. And after we do the matching, then we can do the estimation of the skeleton, the connection. All right, so this is called bottom-up. Please note here that at the current stage, the top-down is more accurate than the bottom-up at the current stage. So that's why many people actually use the top-down instead of the bottom-up if they want to have better accuracy. Okay, so now once we have the key points, the 2D key points, the next things to do is to estimate the 3D pose. Okay, so this is one of the examples in the literature how we can get the 3D pose from the 2D pose or the 2D key points. So given this kind of frames here, let's assume that this one is in 2D, 2D joints, 2D key points. So then from these 2D key points from different time, we sample these different frames or different time to estimate a 3D pose. Okay. So this estimation for one time 3D pose from a few different frames or key points in different times is called TCN, temporal convolutional network. So there is a network here that accepts a few 2D points to estimate one time 3D pose. Okay, so this is very important concept in 3D pose estimation, that people use this TCN as the backbone quite a lot. And we will use this TCN as well in our research here. Okay, so this TCN is actually a published paper in CVPR 19. Right, so the implementation of this TCN is quite straightforward. We have this network as with a skip connection, and then we have this 243 channels and 34 frames. Okay, so that means that we have 243 key points from 34 frames, and then from these 34 frames, we estimate the output, which is one frame with the key points, with 51 key points. It actually in 3D, so you have to divide by 3, which is 17 key points. Okay, sorry, I make a mistake here. Actually, the 34 is the number of the key points for each frames, and then we have 243 frames for the input here. So I mixed up the number. And that one will be the input, and the output will be 3D joints. Okay, so this is the backbone of the TCN, the network for the TCN. And in this direction of work, people normally just train the network in supervised way, because we have this ground truth, and then we can compare the estimation with the ground truth and do the backpropagation. But we can also use 2D poses. Unlabeled means that we don't have the 3D ground truth. Means for this particular case, we need to do the projection. Means that we have a 3D pose estimation here, and then do the projection in 2D, and then compare this in the 2D domain. Right. So this is semi-supervised training of this method. So I will not explain too much about the global position, but the global position is here is basically that we need to, we can also have the estimation of the location in 3D space, because we have the ground truth 3D space as well. Anyway, so this is our work in ICCV and AAAI 20, multi-scale network for 3D human poses. So the first challenge that for this one is that occlusion, especially self-occlusion, can happen frequently. And existing method that I just explained rely only on the raw training data. Okay. Means that there is no mechanism that specifically to handle this occlusion. So this is our framework, our basic pipeline. We have the input video, and we have human detection. Again, this is top-down approach, because this is more accurate. And then we have a key point estimation. Based on this key point estimation, we use TCN. And for 2D poses, so we not only use TCN for the 3D poses, but we develop a network for 2D poses as well. Means that we use TCN to have more accurate temporal constraint on the 2D poses. And then from this 2D poses, more accurate 2D poses, we use we transform the 2D into the 3D. Here there is no occlusion mechanism yet, but in the next slide, this is the occlusion problem, particularly the self-occlusion. And the solution that we propose here is to filter out inaccurate 2D points and then augment occlusion data. So I will explain this a bit more details. So in the 2D key points can be inaccurate. So for example, this joint here can be inaccurate. It can be somewhere here, for example, right? And this joint here can be somewhere there, and so on, because of the inaccuracy in 2D. And this create this error here, inconsistency in terms of the or the incorrectness, inaccuracy in terms of the 2D pose, can make the training process here and training process here in a bad condition, in a bad situation, because the inaccuracy will make the key point highly inconsistent. And highly inconsistent data is bad for network training, for learning. So this is highly inconsistency to the key points is something that we have to deal with here. And the solution for these highly inconsistent key points is just to remove it. So we have to remove this. For example, if you have 17 key points here, for example, and 1 or 2 of them are very highly inaccurate, then we have to remove them. Because again, inaccuracy or inconsistency is bad for training. Okay, so that's our idea here. And how we can know that the key points are inaccurate? We use confidence score. Because we use softmax, we can use a confidence score to gauge whether the key point is accurate or not. If it is below the threshold, then we just remove this out, because we know that this one is inaccurate and inconsistent. That's the first approach. The second approach is data augmentation. The problem is that in our 2D TCN and our 3D TCN needs to have pair data. So if you have 2D points here, we have to have the 3D points here. So, but the problem is that for occlusion, we have the 3D points, but we do not know the 2D points, because in the 2D points, in the first place, there is no data of the 2D points. So there is no way to let the network learn about this data. And in some cases, for example, this data here, the occlusion for the hand here, for example, is not that many in the first place. Right? So there is the problem that we have, the limitation of the data. The limitation of the data for various occlusions possibilities. And in order to generate these various occlusions or occluded key points, then we create our own data. Right? So our own data here means that we do the data augmentation. How the data augmentation is done is as follows. So we have the 2D data here, and then we have the Cinderman model, and we have the key points. And basically, this is how we generate our data. So in this case, we know that actually the ground truth for the 2D TCN is actually here. Right? And the ground truth for the again for the 2D TCN is here. So in this case, if we know the ground truth of the 2D TCN, then we can also train the 2D TCN with our augmentation data. If we don't use the augmentation data, we cannot train our 2D TCN, because simply there is no ground truth for this. Okay, so I hope that makes sense for the reason of this data augmentation. So in the end, we do this combination of the data augmentation and data filtering, and this whole thing is end-to-end. So we have 2D key points losses, we have reprojection losses, and we have discriminators losses. So this is a new additional loss that we add in this paper as well. Okay, so this is the first work, and this is the results. As you can see here, if it is using Pavlov, method, which is the previous method, the occlusion happens here, right? So if you look at this leg here, the leg estimation is wrong, but with our result, it's much better now. So that's the advantage of of the mechanism that we designed for handling occlusions. So as you can see here for our quantitative evaluation, compared to path flow method, most of the cases, our method can perform much better. So for example, 47 point here and then become 42, 65 become 58, and overall 46 become 42 in terms of this evaluation. All right, so I will not show this one. This is just the same result that we, the video result. And the other challenge aside from occlusion is that the size of person or speed of action can vary, and natural poses must be checked both spatially and temporally. So in the previous existing method, all this is just rely on the raw data without any specific mechanism. And especially for the natural poses, it's only checked spatially and it's not checked temporally. Okay, so this is a problem that we have a size of person and speed of action that can vary and not really natural to some extent. And our solution here is using multi-scale features and spatio-temporal KCS. KCS here is a kinematic change space. So the basic idea is quite simple, that we have the multi-scale features. So we don't do the multi-scale in terms of the image domain, but we do the multi-scale in terms of the features. In terms of the features means that the number of the output for each of the features can be different in terms of the resolution. So that's the basic idea of the spatial multi-scale here, because some people can be very small and not really clear in terms of the data, and then we mimic that in our features. And based on this, then we do the training for each of this scale of the features, and we do the occlusion or augmentation as I explained before, and then we do the embedding for all these to have temporal multi-scale convolution. So this one, we have our TCN, and based on our TCN, then we will check with using KCS, a spatial KCS and temporal KCS, whether this the 3D estimation is valid or not. Okay, so I will explain later on soon here about this KCS and temporal KCS. So basically, these multi-scale features that I just mentioned, that we do the multi-scaling in feature domain. Okay. Right. So this is the idea of the KCS. The basic idea is that we have this 3D skeleton, and this 3D skeleton, if you use mathematical manipulation, you can transform this in 3D, and you can have the representation of this skeleton in terms of the length of the bone and the angle of the bones. So by transforming this, the good thing is that if we can have a skeleton, 3D post skeleton like this, for example, and then we transform this into KCS, into this kind of representation, then the network here, which is the discriminator, can say whether this is a real or natural pose or unnatural pose or fake based on this bone length and angle. So this network is specifically will look at the angle and the bone length. And we train this network in such a way that it captures only the natural bone length and natural angles. So P here, the matrix P, will capture the length of the bones, and the other part here is actually the angle of the bones. And if the network can capture the natural angle and natural bones length, then it can be used to assess whether the bone, the 3D poses are fake or real. Or fake here mean unnatural, and real mean natural. So based on this KCS, we develop temporal KCS. Temporal KCS is that we do this operation, mathematical operation here, means that the change of the length of the bones and the change of the angles in temporal domain should be also natural. It cannot be unnatural. I can give you one example. One of the example is the bone. For example, the length of the bone have, even though the rate of the change have to be 0, right? Because the bone cannot change suddenly. So that will be captured by our network. We don't really put 0 in there, but it will be learned by the system itself. But the angle is more difficult to decide, because this one is up to the network to see whether what is the best rate of change for the angles in terms of the temporal domain. Okay, so this is our idea for the temporal KCS, and then we implemented this in our network in this way. So we have the discriminator here that we train using KCS and temporal KCS, and with that we have this performance. So as you can see here, this is the base results that we have, but using our overall techniques, the performance is much better compared to on multi-scale only without our KCS and our temporal KCS. So this is the quantitative evaluation ablation study for spatial KCS and temporal KCS. As you can see here, when we use temporal KCS, the error drops further. And when you use a multiple stride to get the speed and multiple view to get the spatial features, we see there's a drop in terms of the errors, right? So which is a good things that we have here. Okay, so the next challenge is the domain gaps, which is a common problem in deep learning between training and testing. I will not talk too much about this because of the constraint of the time, but I just want to give you a very basic idea that we use unsupervised loss in the testing. So in the testing, we optimize our network using these unsupervised losses. And in this, importantly, we use the reprojection loss here with W. And the W represents the confidence of each key points. If it is not confidence, we can just remove this and set W equal to 0, which we call as hard thresholding. But hard thresholding is not really good, and we use a soft thresholding instead. And it means that even though W below a certain threshold, we just keep that W, the value of W, and then we'll reduce the representation of this reprojection loss. But the problem with this confidence score is that the confidence score are not likely to be linear. So as you can see here, the confidence score is not like a probability or not like a uncertainty. This is a really highly nonlinear. So the x-axis here is the confidence score, the y-axis is the accuracy. As you can see here, although the confidence score is 0.8, the accuracy is actually dropped a lot compared to this 0.9. Right, so the confidence score from softmax is not linear, and that's a problem because we use confidence score as a softmax here in this loss. And because of that, we use calibration, and we use calibration means that we force this to be linear, and then based on that, we, as you can see here, using soft thresholding and weighting factors, the performance is much better. The error is very, very low in the optimization stage, in the test time optimization. And this is the results that we have with test time training. So with this column here is test time training, and this one is without test time training. And as you can see here, the accuracy increased quite significantly. Again, this is another example. So I will skip this one because of the time constraint. And this is another work in triple AI 21 for multiple persons. And we use GCN and temporal PCN combined in this work. So the main challenge in this problem or in this topic is that in multi-person 3D pose estimation, interperson occlusion happen quite a lot. And our idea is that because occlusion or interpersonal occlusion happens quite a lot, we use GCN to estimate the missing joint, the missing key points, or the missing bones. So in GCN, people normally use undirected graph. So in the previous works, they use this GCN in using undirected graph, but we argue that the directed graph is better than undirected graph. Okay, so this is, as you can see here now, the graph become undirected. So for example, if you see here, the arm is invisible because of the speed of the motion, and in our method, we should be able to estimate that part because it's the same as occlusion. Okay, so basically what we propose here is that we have this GCN, directed GCN for joints, for key points, and directed GCN for the bone. For you, we have a bone GCN and we have joint GCN. And then when we have these two, we combine this, and then we can estimate the full estimation of each of the person. So this is the person 1, 2, 3, because there are 3 persons in the input clips, in the input video clips. All right, so that is really the basic idea, that we use the GCN for joint and bone, and our GCN is a directed GCN. And this is the comparisons. If you don't use GCN, or in this case, we use directed GCN, as you can see here, even though this is the person is totally occluded, the legs is totally occluded, we can still estimate the joints in 2D, and we can, because we can have the joint in 2D, we can also have joints in 3D. So that's really the basic idea of the fourth challenge, which is interocclusion. And the next challenge is a multi-person estimation using camera-centric. So if it is in the person-centric, what you see is this one. It's a person-centric. And we have to change the person-centric in multiple persons because it's not possible to show in a person-centric, right? So I will show you a how person-centric look like. So this person-centric look like this one. Because there is no information of the location. So everyone is in the same place. So that's another problem in 3D human pose estimation, because we need to estimate the absolute or the global position of the persons. And in this case, the coordinates should be the camera coordinates or root coordinates instead of the person coordinates. So that's how we do it. We write a mathematical model for this root DCN or camera models for the different location, and we use that mathematical model to train our root DCN. So this root DCN will estimate the depth, and if we have the depth, then we can know the location of the persons. And this one is in the network way, not in the mathematical way. We based on the mathematical model, but we use DCN to estimate Z and F, Z divided by F, which is the depth, the relative depth. And aside this relative depth, we also have the velocity, of the in terms of the location here. So then we can also predict the location in a better way, and can handle occlusion as well. Okay, so in general, we have this GCN, directed GCN for joint and bones, and then from this human-centric, we transform this into camera-centric coordinates using our root GCN, our velocity DCN. All right, so that's the fifth challenge, and this is the results that we have. We have these results here, and we have the results here as well. If you want to know the details of this quantitative evaluation, you can look at our AAAI paper. Okay, so this is a recent CVPR 2001 paper where we combine top-down and bottom-up. So previously I mentioned about this top-down and bottom-up approach. Then the common questions which one is better, right? Top-down or bottom-up? So instead of debating on what's the best for this from these two approaches, we just combine them. We can integrate top-down and bottom-up. So the idea is that we we still have the bounding boxes, but the bounding boxes can be wrong. So for example, look at this one. This is one person and this is the other person. But because the bounding box can be wrong, the second person here is only partial and is included in this bounding box of this person here. So this bounding box is actually wrong, and it can be it can make the estimation of the 3D very wrong because of these unrelated key points. Right? So to solve this problem, we use bottom-up. In bottom-up, we don't really care about the person identity. We only care about the distribution of the key points. And from this distribution of the key points, we can decide the person identity later on using this bottom-up network. Okay, so that's how we deal with this. So how we can combine. So we have this heat map from the detection patch or the detection part, and then we feed this into our bottom-up branch approach, and then we can have the identity of the persons here, and we also have the identity for the person here as well. Okay. So we have two identity of the persons here from the top down and here from the bottom up, and then based on that we use the integration by post matching. And once we have the post matching, and when we do the tracking for the ID of the persons, then we can estimate the 3D. And we, of course, we use the KCS and TKCS to decide to assess whether this is real or fake. All right. So yeah, so this is the result of our approach in comparison to top down and bottom up. And as you can see, the top down can be very, very wrong here. But I think it's much better if you use our combined bottom up and top down. And here the bottom up can be wrong as well. Okay, so this is the last challenge, whether we want to use top down and bottom up, which is quite a debate in the literature. Some people like bottom up, some other people like top down. Again, as I mentioned earlier, top down at the current moment is more accurate than bottom up. But the top down is very vulnerable or very dependent on human detection. Put the bounding box. Okay, so again, this is the end result that we have at the moment, and this is the video that we have. I will show you briefly about this. So this is our estimation here. Okay, so that's, I think, almost the end of our presentation today. So I mentioned about these challenges. Challenge 1, which is sub-occlusions. Challenge 2, which is varying size and natural poses. Challenge 3, which is domain gaps and the respective solutions. And we have a challenge 4, which is a multi-person 2D pose or interperson occlusions. Challenge 5, which is a camera-centric coordinate versus person coordinates. And we discussed the challenge 6, which is the choice between top-down and bottom-up. And for the future challenge, our challenges, we have this crowd scenes instead of multiple persons. We have many persons in the scenes. We also didn't discuss about the speed. Actually, the speed is quite slow. It's not real time yet. And we didn't discuss about degraded image like blur, noise, low contrast, low light, and so on. Imbalanced data, rare pose, rare angles, and so on. Out of distribution poses, right? A new poses, for example, in gymnastic, maybe some people create a new poses that is not in the current data sets. And of course, generalization, how this training data can work across different data sets and scenes. And importantly, also light network for applications. Okay, so this is the research team that we currently have. Yu Cheng from PhD student from NUS, Bowen from Tencent, Ho Yang from Tencent, and myself from NUS. Thank you.
Thanks, Professor Tan, for the insightful talk. It was really interesting. I would now invite all of you to kindly post your questions to Professor Tan in the Q&A box. I would collect them and post it to Professor Tan. So already we have a couple of questions. So I'll just start off with the questions. So, so one of the questions is pretty specific. It's from slide 23. So the question is, must the pairs of 2D poses be in immediate sequential frames? So, so that, I mean, that's a pretty straight question about the technique used.
So what is the question, Jitin?
Must the pairs of 2D poses be in immediate sequential frame?
Sorry, I cannot hear clearly.
Must the pairs of 2D poses be in immediate sequential frames? This is in slide 23.
23, this one, right?
Yeah.
So the answer is for 2D TCN, because this is a temporal network, so we need to have a sequence of data, augmented data. So the augmentation that we do here is in a video clip, in a sequence of frames. We have as I mentioned again, the issue is that in 2D TCN we have input image, but we don't have the occlusions ground truth, and this cylinder model will give us the ground truth for the 2D key points. I hope that answered the questions.
Perfect. Yeah. So there's the previous question was by Kenneth. I forgot to mention the name, and this is by Cathy Chong. And the question is about the ice skating. So essentially, the question is that so given that most of the techniques are developed for detecting motion as far as walking and running is concerned, but then how does it capture the motion of skating, where the motion it's more horizontal, right? There's no walking involved. So how much is it able to capture it?
So that's a good question. So basically, as you can see here, the human detection and key point estimation doesn't depend on the temporal constraint. So whatever the things that is only captured frame by frame. So this one is frame by frame. So our temporal will include this kind of temporal motion. And our motion is actually local motion. It's not really global motion. If we talk about walking versus ice skating, for example, in a global, in 100 or maybe more frames, they will be different. But in one frame to the other frame, it's very, very small. Actually, it's 125 frame per second. I mean, 1 second is 25 frames. And in 1 second, there's not much motion that we can observe. So, well, in other words, the motion, the change of motion, the change of poses is very, very small, very smooth. So if we just apply smoothness constraint, it doesn't matter whether this action is walking, running, or ice skating.
Okay, cool. Yeah, that should be answering the question. So other questions about the cylinder man model. So how important is it in the sense that can we replace it with a different model like SMPL? And what is the significance of this model itself? So this is by correct. Yamazaki.
All right. Yes, any model is fine as long as we can generate the ground truth of this occlusion. As I mentioned again, the motivation of this, the reasons why we do this is because we cannot have this ground truth here, that this is actually occlusion. The green part is occluded. We don't have this information. Without Cinderman model, we do not know whether this green part is actually occluded or not. And this information is necessary for the 2D TCN and later on 3D TCN to be trained, for them to be trained. So how we can get this? We use a cylinder model, but of course we can use SMPL as well, or any other kind of method, as long as we can have this ground truth that this one is actually occluded into the frames.
Okay, good. So this question is by Kenneth. So the question is regarding security access control. So like how much of this human pose can be actually used for human identification? and what are the challenges in doing that?
Yes, that's interesting questions. This one is a bit beyond our research because that one is in the gait or behavior analysis. So as you can see here, what I can imagine if you can have this poses, right? So I will show up again here. So if you can have these human poses and the time motion, then you can train the network, gait recognition network, to know whether this is what kind of action, what kind of problem that, what kind of information that you want to extract from it. So that will be the, so I mentioned that we have 2D pose, you have 3D pose, and then from this 3D pose, you can use this 3D pose for gait analysis or behavior analysis.
Okay. So this question is by Hanlin Go. So the question is about the key point based method itself. That key point based method is gives a very coarse pose estimation. So it gives something like head orientation or hand gestures. So and it suffers from depth ambiguity, especially from silhouettes. So the question is, can you comment on the pros and cons of some methods which are more fine-grained, perhaps something like which blends shapes?
Yeah, so as far as I understand the question is, I think, is more focused on 2D pose estimation. So basically, that's true that in 2D pose estimation, so I will show you again here. There are two approaches, and this one, for example, is very depending on the bounding boxes, and the bounding box can be very, very long, especially in the degraded cases or in the complex scenes. And if you rely on the top-down, then the estimation of the key points will be very bad. Okay, so that's the problem of the top-down, and the problem of the bottom-up is similar. Although we don't really have the bounding boxes, these key points here can be incomplete, and in some cases we do not know how this is the head here have to connect to the shoulders here. All this head here have to connect to the shoulders here. So in other words, we do not know. If it is very complex, we do not know which point have to connect with the other points. So this is still a challenge. That's why in the integration of bottom up and top down in our CVPR paper, we try to resolve this. We try to resolve this using a combination of these two approaches. And this is will be in CVPR 2001, and in that case, it will be the state of the art, because the performance is not specifically for the 2D. We are in this paper, we are dealing more or focus more on the 3D. And in 3D, we can claim that our method here is state of the art in terms of the performance. So now, answering the questions, what are the specific methods that for pros and cons? I think there will be a lot of methods in 2D to mention that. Maybe you can start looking at our papers, because we list the methods in our section, in the related work section.
Okay. So this question is by Augustine, and this is about the scalability of the technique itself. So how much is the time difference of rendering a 3D pose when compared to existing 2D pose estimation techniques like open pose? And how much does the size of the crowd impact the time of estimation itself?
Yes, so the speed is actually very much depending on the accuracy as well, how much accuracy that you want. So for the original Pavlov's method here, actually this is something that the basic pipeline. From the key points, as long as you have the key points, then it will be the estimation, the 3D pose. So in this Pavlov's method, they use 243 frames. So it means that there is some delay, because if you divide this with 25, right? It's basically you need to have around if you have to 4-second delay there. around 4-second delay in terms of the pose, right? And this one is a very much a backbone. I mean, it doesn't do anything much aside from just converting 2D to 3D. But even for this one, there is a delay in terms of the estimation. Right? And another delay is because of this process. This one is basically this network. This network need to have some process to do as well, aside from waiting for the buffering of the 243 frames. Right? So this one is a very basic backbone, and it takes some time. And even more, and when we apply our framework, so in the end, this one is our framework. So as you can see here, the CVPR framework is much more complex than that, because aside from the TCN, we also have GCN. So the bare minimum is TCN, and then we have GCN, and then we have the combination of the post-integration, post-matching, and we also have the checking whether this is a real or fake. So I would say that this one is the speed is really a constant. We cannot have the real time at the moment, but again, it is a trade-off between speed and accuracy. If you want to be accurate, I would suggest this framework. But if speed is very important, then maybe start with Pavlov's method will be better, because there's a bare minimum of using DCN.
This question is by Biswanath, and there are two questions actually. So one is from a security perspective, as in how much of this technique can be used for detecting an intruder based on the pose of the person who's entering a perimeter. And similarly, the other question is like how much of this technique can be used for detecting fall for an elderly person.
That's right. So this is the application that I mentioned earlier, which is a video analytics. One is about fall detection, and the other is a crime detection. This is similar to what I said before in this framework, in this pipeline. We have 2D post estimation, we have 3D post estimation, and once you have the 3D post estimation, you can use them as the input for your network. This network can be fall detection, this network can be crime detection or behavior analysis. And then the output is really up to you. Maybe this is the categorization or classifications in terms of whether this is crime or not crime, whether this is fall or not fall. Right? So that's the idea, that we have 2D, 3D, and application. Application here can be crime classification or can be fall detection.
Yeah, so thanks. So now I guess we are running out of time, so we'll just conclude with one more question. So this is like, so how much of this technique is amenable to privacy preserving, in the sense that how much of obfuscation can this technique handle?
Yeah, that's really a good question. We haven't get into that point yet at the moment. Again, we just finished the framework up to the 3D post estimation. And what's next should be the application of this into the privacy. Because in the privacy, then we can say whether this is, again, something that have to be protected or not to be protected. Right. So, and the privacy here is can have many different meanings, because is someone walking and the walking normally on the street, for example, I don't think that there's any much privacy have to be preserved there, right? But if some context, the way people walking can be identified further with the identity of the person. So if that's the case, then it will become in the privacy domain. So as that will be the things that we want to look further, how these poses in terms of the motion can be used to identify the identity of the person, or can be identified to action that people don't want to reveal.
So yeah, thanks all for the questions, and let's thank the speaker once again for the interesting talk and the lively discussion. And thank you everyone for the questions you have posed. So a presentation is only as good as the discussions we have later on. And thanks for having the lively discussion which we had just now. So we hope all of you enjoyed the webinar as much as we enjoyed hosting you. So should you have any questions from today's talk, please do contact us at NCRiPT. The email and the web page is displayed on the screen now. So thank you again. I hand over to Brian for any further announcements. Thanks.
Okay, thank you so much, Jitin. I would like to thank all our speakers today, Robby and Jitin, for sharing their valuable insight and knowledge. I also like to give a shout out to NCRiPT and Lini for their help in organizing this event as well. And also thanks for our audience today for engaging with our speakers and sending in your questions. So for our audience today, do take note that we'll be sending out a post-event email with important information, including a recording for this webinar. So do keep an eye out for that. And so with that, we've come to the end of our webinar. Thank you all for spending your Wednesday morning with us. And on behalf of SGInnovate, I would like to wish you all a great week ahead. And we look forward to seeing you again at our next event. Bye. Thanks, Jitin. Thanks, Robby.
See you. Bye. Thanks.